Okay, we got a nice optics practice test here to go through. It's actually a real old test from before, but this looks like a grade 11 question. It says the green laser with a wavelength of 532 nanometers is shot into the water. What's the wavelength under the water? So it's going to shrink by that factor. So we can say lambda in the water will equal what it is in the air divided by 1.33, because that's the amount of the speed, the factor of the speed of the light slows down, 532. Comes out to exactly 400 nanometers. Okay. What property of light could the wave theory not explain? Waves need a medium to travel, so traveling through space. Or a vacuum, whatever. You're missing there's no molecules to carry it, so they were coming up with they tried to say there was ether out in space that we couldn't see. Start talking about magical substances, and you know the theory has a flaw. You got some polarized lenses at the store. How can you test if the glasses are real? Well, polarized lenses, they look like, if these are your glasses, they're super fine. They look like vertical filters like that. They only let vertical light through, and when the sun shines on the road, the vertical beams hit the ground and get absorbed in just the horizontal come up. So the bouncing off the surface filters out the vertical. This one only lets vertical through, so it filters out the horizontal. These glasses would remove all the glare. But this question just says, how can you test them? If I took two pairs of glasses and put them in front of each other, like here's one pair, and then I put the other pair on top of this one. So these guys, vertical filters, this one in the background is vertical. This one that I have here is sideways. Okay, if this blocks vertical and this blocks sideways, nothing gets through. This would turn black. Nothing would get through as you tilt it back and forth. Okay, what experiment proved that light was a wave? You need to give the scientist's name. Well, that's right here. Young's double slit lab. That's the one where we had the slit, the light waves come in here. They're perfectly in unison. They travel through here and they travel out like a source. And when they hit the wall here, that beam goes straight to the wall. That beam goes straight to the wall. They have exactly the same distance to go. It'll make a bright spot. Because both waves, say this is wave A on the top, B on the bottom. Okay, they're traveling in unison. Oh, that's not a very good diagram. Okay, the peaks are all lined up. Even when they hit the wall. If we shift it a bit, this spot here, one wave is delayed because now A takes a little longer to get to the wall than B, and you'll get dark spot. But the only way you could have interference like that is if it was a wave. If you're just bullets, the bullets would make two dots on the wall like a perfect shadow. Okay, sketch the interference pattern of single and double slit. Okay, let's do double first because that's the first one that they did. Here's a double slit. On the wall, we'll get equal size bright dark spots. Okay, the one in the center is bright because they both have exactly the same distance to go. This one here, that one's going to be dark. D is the distance between the slits. Remember we did the note, there was a path difference here. And we go D sine theta equals 1/2 lambda for dark. Okay. And for bright, let's see, the bright one here in the middle here. Well, this could go up. It could be also a lambda, 3/2 lambda. Okay, and if we do bright, 0, if there's path difference is 0, it's bright. If the path difference is 1 full lambda, hey, what's going on here? Oops. It's 1/2 lambda, 3/2 lambda, 5/2 lambda. It keeps going up by a full shift of a lambda. This one goes up from 0 to lambda to 2 lambdas, etc. Okay, and for a single slit, on the center wall there's a super bright spot, and then the rest of them are smaller. And this one fades really fast. Oh, we could call this here. Let's see. Might as well put all the terms on this one question. I'll recap everything. Here they call this 2 delta y, and this one will just be a delta y, and this is in D, this will be a W, which means the width of the slit. Okay, so if we look at these factors, everything will be reversed now. So the bright spot will be d sine theta equals half lambda, 3/2 lambda, and dark is where it used to be bright. So dark, d sine theta equals lambda, 2 lambda. Okay, and in the center where 0 was, it's not dark because 99% of the light's going to go firing right through there. So you should, if we just looked at the interference pattern, you'd have like 2 equal sized ones there with a dark spot in the middle, but all the light goes through, makes it super bright. That's only a 2-mark question. If it was a 4-mark question on your test, then you'd have to do all this extra explanation. Okay, student performs a double slit experiment using a slit separation of 27.6 micrometers. So that means D equals 27.6 times 10 to the minus 6 meters. Screen is placed 8.5 meters away from the center of the source, and the distance between the nodal points is 18.5 centimeters. So delta x, okay, which is going to be 0.185 meters. Find the wavelength. Okay, well, we got delta x equals L lambda over D. We have everything except for this guy. So you could put all the numbers in. Length of the room is 8.5. Lambda's my unknown. Distance between the slits is, and lambda, I have to figure that one out. So I got 0.185, 27.6 exponent 6 times, divided by 8.5. I get 0.0000, I better change the scientific notation. I get 6.007 times 10 to the minus 7, which would be 601 nanometers. Okay, light from a monochromatic source passes through a single slit. The width is there, so now we got width equals 14.7 times 10 to the minus 6 meters. If the central maximum is 5.5 degrees, so here's the slit, here's the center, and they're saying this angle created by the central maximum is 5.5 degrees. For the whole thing, I just need one of these angles here. So then my theta would be just the one side, so I'd have to go 5.5 divided by 2, that's 2.75. And this is the first dark spot. Okay, so we can go back here. Single slit, the first dark spot lands at a full lambda. Oh yeah, these should be W's then. Same pattern, but it's just a single slit. So I go W sine theta equals, for the dark spot, is a lambda. And what are we looking for? We're looking for wavelength. So we have width, sine, it's only half the angle though, equals a full lambda. So now we got 14.7 and 2.75 sine, better make sure I'm in degrees. And I get some crazy small number again. Let's put it back in scientific notation. Or we can just leave it in nanometers. 705.3 nanometers, or just 705. Significant digits is really only 3 or 2, so you should chop it off. But. Okay. A single slit interference pattern using blue light with a wavelength of 450 nanometer creates a central maximum 8.5 centimeters wide. If the slit width is here, how far is screen? So we're looking at the same formula again. Well, we're going to use the delta y one now. And delta y, they're looking at the wall. There's a central one, and they're saying the central maximum is 18.5 centimeters. But that's 2 delta y's. So delta y would equal, I guess, 9.25. 18.5 divided by 2, 9.25 centimeters. Divide that by 100. Okay, we got delta y. Look at the width. We got the wavelength. The only thing we're missing here is L. Let's fill in all our numbers in. The wavelength is 4. Might as well write it up full so we understand what nano is. A nano is 10 to the minus 9. Oh, but I always want to write down, well, you get to know that it's always going to be 10 to the minus 7 with 1 decimal spot. The width, it's 15.5 times 10 to the minus 6. I have to solve for L now. So I can type in, there's my meters. I'm going to multiply by 15.5 exponent 6 negative. And then I'm going to divide by 4.5 exponent 7 negative. And I get 3.186. So 3.19 meters is the length of the room. Next one, diffraction grating etched was 28,000 lines per centimeter. So if I want to know how wide one distance between the slits are, I would have to go 1 centimeter, which equals 0.01 meters. And I'm going to slice that into 2,800 lines. So if we go 0.01, 2,800, divide that, might as well go scientific notation, 3.57 times 10 to the minus 6 meters. That's going to be your D. The distance between the slits, you got the wavelength. What's the angle to the first order maximum? So the first order maximum is going to be D sine theta equals 0 was the center. The next maximum is when the two waves are still in phase, but they've both been shifted apart by 1. So we're going to find this angle here. I have D. We have the wavelength. So you can start put in the numbers here. So 3.57 times 10 to the minus 6 sine angle equals 5.85 times 10 to the minus 7. And we're going to find the angle. So I got that number's on my screen, so 5.85 exponent 7, change sign, divide. And then we're going to inverse our sign, get out of scientific notation. Inverse sign, oh, hold on, we got an error. Negative sign. Oh, I did the wrong way. 5.85 exponent 7, divide by 3.57 exponent 6. Now inverse sign that. Then we get 9.4 degrees. Okay, explain how a pattern of a soap film from a vertical loop held vertically on the surface of Earth would look, and then compare it to how it would be in a space station. So the main thing different here in the space station, there's no gravity. But if I took my hoop, there's your little hoop or wire that you're going to dip into the bucket of solution, and then we're going to pull it out. Okay, there it is here, and it's going to have all this soap in there. Okay, on Earth, if we did a sideways view, cross-section view, here's what the bubble would look like. There's the ring at the top, here's the ring at the top bottom. It's going to be super thin at the top, and it's going to get thicker at the bottom as gravity pulls that bubble down to the bottom. Okay, so it says, compare one held vertically on the space station. This is on Earth. It's going to be fat at the bottom and thin at the top. On space, it's probably going to be all the same. The top and the bottom will be perfectly the same. I'm probably leaning more towards that it's probably going to get thicker at the ends and then thicker at the other end and thin in the middle because surface tension is going to pull it up. Remember doing the graduated cylinder? You got a graduated cylinder and the water creeps up the sides and you measure from the meniscus. So that's water surface tension pulls it up the surface. So I think it's probably going to do like that also. But let's take a look what happens here. So I'm going to send light here. Light's going to bounce off the surface of the bubble to my eye. And then it's going to go in and bounce off the back of the bubble and come out to my eye. And I want to know whether it's going to, and this would be when T equals 0, when it's super thin at the top. Is that going to be bright or dark? So let's take an expanded view here. Here's the bubble. It's mostly water, so the index is going to be around 1.33. First beam bounces off the bubble, goes to my eye. That's a hard bounce, so it's going to shift by half a lambda. The next one's going to come back to the back, we're back into air again. So that's a soft bounce. Absolutely nothing happens from bouncing. And it comes out here. And the only difference there is this guy had to travel an extra thickness in and a thickness out. It's either going to keep him in phase or put him out of phase. I'm saying what happens if the thickness is really, really thin? Then that means the first beam, if you call it A, it shifted by half a lambda, and B did nothing. So if we look at it, here's an original sine wave. Say this is the part where it hit the wall, right here. So if this A beam was coming in and hit the wall, and it shifts, that means beam A is going to be right there. If the thickness is super zero, beam B does nothing, and they're out of phase. One's up, one's down. So then this would be dark at the top. So this would be dark here, and then you'd get all your rainbow colors here. Rainbow of colors on the bottom. Up in space, it might all be the same color, or dark in the center with a rainbow color on the sides there. Okay, let's take a look at that question. In order to verify a certain manufacturing process, double slit apparatus, the laser producing, okay, quality control, we got the wavelength. Manufacturer claims that. So that distance between the slits is really an unknown. We got the first and fifth nodal lines on the screen. Nodals are the dark ones. So we got to look at 3.5 meters away. So what do we know? Lambda is 6.328 times 10 to the minus 7 meters. The length of the room is 3.5 meters. D is what we're ultimately looking for. And I need to get delta x, and then we can use the formula. Delta x equals L lambda over D. And we'll solve for D. But I need to get delta x. It says between the first and fifth nodal lines. So if I look at the point here, say this is the dead center. Here's the first nodal, 1, 2, 3, 4, 5. It's here. So this is the first, and this is the fifth dark band. But how many spaces is there? 1, 2, 3, 4. 4 spaces. 1, 2, 3, 4, 5. And there's only 4 spaces, so that's, and it's 56.9 millimeters. We're going to have to divide that up by 4. 56.9 divided by 4 millimeters, which is 1,000 of them in a meter. So that's 0.014225. And we can put everything inside here now. How am I going to squeeze this? This happens when you write too big. Delta x. 4225 equals L 3.5 lambda 6.328 times 10 to the minus 7, and we're solving for D. Okay, got that numbers on the screen. Divide by 3.5, 6.328 exponent, divide by that, flip it over. And I got 1.5569 times 10 to the minus 4. If I change that to micrometers, which is 10 to the minus 6, that's going to be about 155.7 micrometers. Is that in 3%? Let's see. 155.7 divided by 135. I mean, minus 135 is a difference of 20. That's 15% error. Okay, so I'm pretty sure you're outside the range. Okay. Okay, construction company wants to do an office tower. So here, okay, this will be the glass. And it's 1.52. And this will be air out here. And it goes 1. And the coating, it's 1.15. Okay, so that means the light's going to come along here. from the sunshine, whatever it is going to bounce off the first surface. Let's call that beam A. 1 to 1.5 is a much harder surface. It's going to flip by half a lambda. So on the wave, it's going to bounce from a positive to a negative. The beam will continue into the coating and come back out here. So the coating is going to be T thickness. Again, it's another hard bounce because it went from 1.15 to 1.52. So it's going to shift by half a lambda, which keeps them both together. But now the thickness of the glass is going to be a factor because this beam is going to be time delayed to travel in and travel out. Minimum non-zero thickness, you always have to put that in because zeros could be one of your answers. And in this case, it would be. If 0 was there, if there was no thickness of the glass, the two beams would still be together. Okay, so I want to know the next time they're together. So, bright would be at T equals 0. Get rid of that comma. Bright would be T equals 0. And then you could add, and then the dark would be at quarter. So T equals 0 or half wavelength. Because if this is a half a wavelength, in a half and out a half is a full shift, and a full shift puts you in the same spot again. So the second would be lambda. So if I look at that, if I look at my graph, here's our nice little light wave coming in. It hits the surface right there. So that would be my separation. Beam A immediately goes to here. Beam B, if T equals 0, beam B is also there because it does a half a shift. If T is a half plus a half is a full shift, it would put B over here. If that's lambda over 2. Okay, so that's one we're looking for here. Hold on, what did I write down? Okay. So lambda over 2 would also work because it would go in a lambda over 2, out a lambda 2 is a full shift, and they'd still be together again. So let's find out the wavelength in the coating is, we want the blue, 475. But inside the coating it's 1.15. 475, 1.15 is 413. And we're looking for half of that. So thickness equals lambda over 2 is 413 divided by 2. And I get 206.5. Okay. That would be the thickness of the coating, and the building would have a nice, pretty blue color to it without any real paint or anything on it. Okay, we got an air wedge. Single sheet of paper with 18 dark fringes is 1.66 centimeters. So again, you're back here again. These are the dark fringes, and the distance between these dark fringes we call delta x. The formula for an air wedge is delta x equals L lambda over 2t, and t would be the thickness of the paper. But they're saying there's 18 dark fringes. So there's 1, 2, 3. You can see though that between the dark fringes, it's always one less than no number. So this would be 17 spaces. .66 divided by 17 is 0.0976 centimeters divided by 100. 1, 2, 3, 9, 7, 6, 5 meters. Okay, we got delta x. We got the length. The length of the glass is 0.187 meters. Got the wavelength. 540. Lambda equals 5.4 times 10 to the minus 7. So we have that. The only thing we're missing here is t. So we have to solve for t. So let's put all our numbers in here. 1, 2, 3, 9, 7, 6, 5 equals the length of the room. Or not the room, sorry, length of the glass sandwich. All over 2t. Okay, so I got that number on the screen. So I'm going to multiply by 2, divide by 0.187, and divide by 5.4 exponent 7. And then invert that. Let's change it to scientific notation. Okay, the thickness is 5.17 times 10 to the minus 5 meters.